Hello, everyone, and welcome to 2021 and the Ideas Seminar. Today, we're absolutely delighted to have as our speaker, Osman Yağan. And I'm sure, and if you're on campus, I would say, and many of you have seen him around. Um, and he's one of the founding members who's been involved with ideas right from the get-go. Let me go in here. Sorry, I'm having some technical difficulties, so sorry, excuse me. Osman is actually an associate professor in the electrical engineering department. He's also associated with Scilab, and he's also one of the CIT, the Carnegie Institute of Technology, the Engineering College's early career fellow. Today, what he's going to be talking about is his work on the effects of evolutionary adaptations on spreading processes and complex networks. So, Osman has this kind of love relationship with very complex networks, how they evolve, change, adapt, how ideas move and diffuse through them. And so therefore, how things like, disinformation and so on spreads through these kinds of networks. His work has looked at lots of different kinds of networks, and he's also looked at issues related to complex networks in terms of not only how do you model them, but how do you evaluate the performance of systems from this kind of complex network perspective. He applies these to things like wireless communications. He applies it to random graphs. He applies it to social media data, and so on. So lots of different aspects. And with that being said, I want to turn it over to Osman. So Osman, thank you very much for joining us today.
Thank you so much, Kathleen, and thank you so much for all the attendees. It's a pleasure to be here. In advance, I apologize if my energy seems low. I'm coming from teaching for 2 hours, so hopefully my voice is gonna keep up until the end of this talk. So as mentioned, I'll be talking about this particular piece of work we did on the evolutionary adaptations on spreading processes. And this is joint work with a number of people, former students, Rashad Elitribi and Yong Zhuang, along with Kathleen Carley, Vincent Poor from Princeton, Anirudh Sridhar from Princeton as well, and Simon Levin from Princeton, and Joshua Plotkin from UPenn. And the work is supported by the National Science Foundation and Army Research Office. So the two things I think that most of us have been thinking about in the past year or so, if not longer than that, I think have been both about spreading processes. One aspect is spread of a virus, which may, as we have still, unfortunately, we are still experiencing, which may turn into a pandemic. And also the spread of information or misinformation that may lead to not so pleasant events that we have all recently experienced, riots, extremism, and so on and so forth. And these types of spreading processes, either spread of a piece of information or spread of a virus, can happen, over large scale of geographical areas. And there are many ways to perhaps model and analyze and get into the crux of what is actually happening. And I'm not going to sort of talk about which option or which technique or method is better with respect to which one, but I like to make the case for the approach that we typically follow in my group based on mathematical modeling. And the idea here is that, and I am assuming with Ideas Center being the host of this talk, many of you are interested in purely data-driven works, but there is still maybe potentially some benefit of mathematical modeling to gain a fundamental and broader understanding of the spreading process. And potentially this approach can lend itself to have some use in developing mitigation strategies. If we have a good model of how things spread, we may be able to perhaps better pinpoint the strategies that will change the course of this spreading in the way we want it to be. If it is the viral spread, we like to maybe slow it down as much as we can. And similarly for maybe the spread of misinformation. of course, if it can be an information that we would like to spread, something that's like democracy is a great thing. Also, you can argue that mathematical modeling can help you better spread or find better ways of spreading such information as well. So the main aspect of my work is about mathematical models of spreading processes. And I particularly like to focus on the impact of the underlying network structure or the contact structure. So if you think about it, when something is spreading, the focus usually is on the modeling of how this spreading takes place. If some person has a piece of information or a virus, how do they maybe pass it on to another individual? But sometimes what is overlooked is the entire big picture of the network structure, who is connected to whom, and how this entire topology of the contact network is maybe playing a role in the way things spread, the speed at which they spread, and potentially also how we can stop that spread or affect it in the way we want to affect it. And my goal, my overall research really has been on revealing the interplay between this propagation, virus information, and so on and so forth, and the underlying network structure over which this spreading is taking place. And today I'd like to talk about a very specific work that we completed actually before the COVID-19 pandemic, and suddenly, unusually perhaps for some of my other work, it became relevant immediately. So this is about the effect of mutations on the spreading process. And before we started this work, we observed that most of the literature assumed that the propagating object, again, I just keep it broad, it could be information or a virus, is transferred across the nodes without going through any modification. So whatever you take from someone, you just pass it along as is, which obviously is not the case. If you are talking about pathogens, viruses, we have seen that they can mutate, and most of these mutations may not make a difference. So you may even want to ignore those little variations. That doesn't really change the course of the spread. But we have seen recently, even for this COVID-19 pandemic, there has been observed variants, observed alternative strains to what essentially has been spreading for several months. That made a big difference, right? People talk about the UK variant or the South African variant that could potentially be much more easy to transmit, to be transmitted between individuals. And also maybe there are studies that show that they could be also more deadly or more likely to sort of lead to hospitalizations of the people. And there are also concerns about whether the vaccines that are currently in place, whether they will be useful against those variants as well. So it's totally, a misleading effort, if you will, to consider a propagation process, consider a spreading event without taking into account the possibility that things can change, can mutate, and that could make an impact on the overall transmission process, overall spreading process. And we can also see that this can be the case for information as well. When I receive an information over one of the social media, I could potentially modify it before posting it, before retweeting it, and so on and so forth. Again, to give current examples, pathogens constantly evolve due to medical interventions, changing environments, and randomly they mutate. But like evolutionary biologists will explain in more details why certain types of mitigation strategies, even the existence of vaccines, can perhaps pave the way to more and more mutations taking place and changing the course of the pandemic. With respect to information evolution or the mutations that take place in the course of a misinformation campaign or an information propagation process, I am giving here one example, and admittedly, it's not a very concrete one where we specifically showed that someone picked it from someone else and modified it. It's not as concrete as an example, but one could argue that So this is an example from the Arab Spring. Some demonstration has been happening near the presidential palace. So if you view that fact as the true source of information, strain one, so to speak, people are presenting it in various different ways. There is no one strain. There is no single way of presenting this information. And how you present it can make a big difference in how many retweets you will get or how prevalent these information or these tweets will be. If you say it's nothing to be scared about, it's a peaceful thing, doesn't even have so many people, the attention you will get or the number of tweets you will get will be very different potentially from the case where you tweet, oh, we have to really save the country, the army has to intervene and the country is about to explode. And the argument here that like how we argue is basically in general, when information is propagating, we should potentially consider the ways people modify the fact, and perhaps there's an incentive to exaggerate, perhaps maybe shape the facts a little bit to get more attention. And potentially after multiple chains of modifications that individually are not super harmful, you may not call or flag them as misinformation, eventually may lead to misinformation as well. So we like to just point out this fact without maybe going into too much details, that even in information propagation processes, we should be able to like look at this from a perspective of multiple variants being spread simultaneously, and each with a different types of transmissibility or the likelihood of being transferred from one node to another. So those are the kind of high-level motivations of this work. And in line with my overall research that always focuses on the impact of network structure, we wanted to now extend this to understand interplay between the spreading event, the propagation process, the network structure, but also now with the evolutionary adaptations, the potential mutations that can take place as the spreading process is continuing, and the impact of it in relationship with other variables involved. So we can outline maybe a number of questions. One question is, how does the existence of multiple variants affect the speed and scale of an outbreak? And a number of interesting questions arise. If a pandemic is almost controlled, but suddenly a very highly transmissible, contagious variant emerges, how does this change the rest of the propagation? And what patterns of mutations, you can ask, are most effective for a given network? Are there specific contact network structures that facilitate these emergence of multiple strains? Or you can also ask the separate question of, if there are variants involved, should you be more aggressive in maybe suppressing the contact structure by closing schools or maybe stay-home orders and so on and so forth to basically eliminate as many links as possible to prevent these new variants to spread to a large fraction of the population? And similarly, again, you can sort of ask the question of like whether mutations are just happening independently, or there is the impact of the underlying network structure as well. So here we are not like really trying to ask the biological question of mutation. So more important question is that like, okay, mutations happen at their own pace, maybe randomly, but what is being selected and becomes prevalent? Could there be a relationship between the network structure and that? Is the third question. So we started with these big questions and narrowed it down to a simple model of spreading processes with mutations. And there was really very little work on this domain before. And so we wanted to handle this problem first. And there's a bunch of ongoing problems, ongoing work in our group on this topic to further extend this particular paper. The model is pretty simple. We say the process starts with a single individual infected with strain 1. So this person was unfortunately infected. And the strain 1 is associated with this transmissibility parameter T1, which is viewed as the probability that independently this red person is going to infect each of their contacts. So for each of them, there is T1 probability that infection will be transmitted. And what is different in our model is that after this event happens, let's say out of the 3 contacts that this individual had, 2 of them got infected, we assume that there is potentially a mutation that happens in this particular person's body as virus replicates, maybe some random changes happen, and this person now has a different strain. In the case of information propagation, you say this person's tweets reached 2 out of its 3 contacts, and one of them decided to change it before tweeting about it. We model this change and mutations using a mutation matrix. And in the most general case, let's say there are n possible versions of this spreading item, information or virus. So we have to think about an n by n mutation matrix. So mu ij, any item here, is the probability that someone receiving item I, strain I, changes or mutates it into strain J before transmitting. So of course, the general case here doesn't mean that all of these entries are non-zero. So you can imagine that in the virus spread, there is no going back to the original strain. So strain 1 can mutate into strain 2, but it wouldn't go back to strain 1. And with information, you can also maybe make certain observations. So I just wanted to present the most general version of this mutation matrix, but in reality, you can of course assume most of these entries are 0 and only some non-zero entries exist. So mutations are assumed to be taking place independently. Everybody within their body, within their own personality or life, goes through this change. They may stay, of course, with the same strain they received with this probability, but with some probability they go through this change. And as a result, the chances that they transmit something to their contacts is potentially different from the probability that they had taken the information or disease in the first place. So in this particular case, this person is mutated, so their transmissibility changed to T2. And you can imagine, you can make very interesting cases where T2 is maybe much larger than T1, which is the case with very contagious variants emerging. Or it could be the opposite case where this person, either converted the information to something very uninteresting and the transmissibility is dramatically reduced. All sorts of things can be captured basically in this generic domain, in this generic formulation. And the overall propagation process, this is of course a very simplified picture, but imagine millions or hundreds of thousands of people being involved in this. The analysis of the spreading process tracks this entire thing. Somebody starts the propagation. They have their transmissibility. So we look at how many of their contacts get infected. We go through the mutation process individually for each person, and then look at how many others they will infect, and so on and so forth. And we stop when no single other person is infected. So eventually, the propagation process stops. And we are interested in a number of quantities. So the number one thing is, under what conditions, we like to know under what conditions this propagation process will become a big deal, will become like the COVID-19 pandemic, will become this meme in the information propagation domain. Something prevalent, something a large fraction of the population gets exposed to. Those are called epidemics, pandemics, and in the information case, again, memes maybe. But there are the opposite cases where it really doesn't go into many people, and we call these self-limited outbreaks. And again, the important question is, given all these parameters, right? We have the network structure, we have the transmissibility of individual strains, we have the mutation matrix. As a function of all of those, can I say something about the chances of this spreading becoming a pandemic or a self-limited outbreak, which we call as the probability of epidemic, or the second quantity. And the second quantity we are interested in is when this thing is going to become a big deal, it's going to be an epidemic, let's say, we are still interested in the size, exact fraction of the population that will get informed, misinformed, or again, in the viral case, they will get infected. So is it going to be 1% of the population or 10% or 99%? So that's the question asked by the epidemic size. And we are interested in both distinguishing cases where it's an epidemic versus self-limited outbreak. And also we are interested in the exact size of the population that gets infected, let's say. So our contributions for this line of work are published in the PNAS journal, Proceedings of the National Academy of Sciences. The publication date is March 2020. And as you can imagine, the actual paper was completed a little bit before that. So the pandemic had not started. So just full disclosure, we didn't do this work knowing that the COVID-19 is around. Just happened to be the case that it became immediately relevant with also recently the mutations. We feel like it was a timely piece of work. So the contributions of the work are, again, the two metrics we talked about, the probability and epidemic expected size of epidemics have been analyzed and obtained accurately under different network model assumptions. There are some interesting observations in the paper about the interplay between the mutation schemes and the network topology and the final epidemic size. How is it affected? I'm not going to talk about this today, but we also spent quite a bit of time in understanding the impact of co-infection. Like what happens if a person or an individual can be infected by not just one strain, but multiple strains simultaneously. So this was also discussed in the paper. And one of the big important punchlines of the paper is that if you look at the classical models that do not have the evolution mutation concept built in, the predictions they have for the final size of the epidemics will be largely misleading. They will in most cases be inaccurate, incorrect. And if you want to sort of get more accurate understanding of the spreading process, you should take into account the potential mutations and use results such as those provided in this paper. So that was sort of the core finding. So admittedly, most of the results are like quite technical and mathematical. So I won't go into all the details, but I'd like to present maybe a subset of the result that I think is a little easier to sort of present in a setting like this. So the main result about the threshold of epidemics, so what distinguishes cases that are just leading to a self-limited outbreak, like not too many people get infected versus something becoming a pandemic, is going through this equation. And you may have heard about this notion of R0 that epidemiologists very frequently use. So the crux of it, R0, is a quantity that says how many additional people on average you will be infecting if you just happen to receive the infection right now, how many others you will be infecting. So in traditional studies of epidemiology, you obtain this quantity as R0. And the key thing with R0 is it's so nice that if R0 is larger than 1, you expect things to go bad, like many people getting infected, and it's getting more and more as time passes. Whereas if R0 is strictly less than 1, you expect things to slow down and die out pretty soon. So not too many people would get infected if R0 was strictly less than 0. In the traditional case, you have this quantity representing R0. So it is the transmissibility of the disease, the chances that one node is going to spread the item to the other. times a quantity that's about the network contact structure. So K is like the number of friends or number of contacts you have. So we are looking at the average of its square minus average value of that divided by the average. And if the number of friends that each person has was Poisson, distributed as a Poisson random variable, this quantity would just simply be the average degree, average number of connections that each person has. So if you are connected on average to 20 people, and this virus had more than 5% chance of basically being transmitted from an infected person to a susceptible one, R naught would be strictly larger than 1, and we would see a pandemic. So that's kind of the idea. And the main result we have obtained says that the impact of the network doesn't change at all. So it is still the same quantity. But what was T, a simple probability item, the transmissibility item, is now changed to this, which may look a little complicated, but it's really just the multiplication of the transmissibilities and the mutation metrics. And then you take the largest eigenvalue in absolute value of that. So rather than T, you basically see that this item, let's say whatever it is that's computable, replaces that. So the crux of the result is this, and this immediately leads to the following question. So you analyze this complicated model, gone through a lot of maybe mathematical derivations to figure out how these mutations change the entire spreading process. But the result you are presenting suggests that it could have been done in a much more simple way, right? You could have just changed this T with this quantity and just follow the literature, the classical literature that doesn't have mutations, and just borrowed every single result with just simple change of parameters. So that was actually a possibility, and we observed that and we tested that. And it turns out that that approach wouldn't lead to correct results, not in general at least. So the process of replacing your transmissibility with this maybe more complicated term is going to be okay in determining perhaps the threshold, like the value at which things will be going from a self-limited outbreak to a pandemic, but it won't give you the exact probability that this will happen. It won't potentially give you the exact fraction of people that will get infected and so on and so forth. So the plot here is basically showing as a function of the mean degree in the network, mean number of connections that each person has, what is the probability that this will become an epidemic. And these types of plots I think are pretty useful because kind of shows you what you need to do, right, as an individual, how much you should reduce your number of contacts, or how much everybody has to reduce their contacts to slow down the spread of this particular virus or this particular information. And it kind of shows you over the various maybe potential network structures, under what conditions you will see certain things becoming very widely spread versus, again, not so widely spread. And these plots are, of course, obtained under a specific transmissibility of the item. And if you change that, you get a different curve, but the results enable plotting this under any setting. And you could potentially, of course, plot them as a function of transmissibility if you fix the degree or the contact structure of the network. So one question here was, of course, we tried just synthetic topologies. We didn't really do our analysis over arbitrary networks. So these were very stylized network models where the degree distribution is fixed. So I tell you the chances that you will have 1 connection, 2 connection, 3 connections, and so on and so forth. And with that information, I generate a random network that's uniformly distributed among all networks that obeys that same degree distribution we started with. So at the end of the day, it's not something that's physically there in real world, but it enables understanding the impact of degree distribution, understanding the impact of the average number of connections on the spreading process, and so on and so forth. But the main question was, is your work any useful in real networks, right? So what if the network structure was taken from Twitter or from some high school whose network structure data is publicly available? And the answer to that turned out to be that we didn't match it as perfectly as we matched synthetic data, but we still came pretty close, and in particular, much closer than what the traditional studies of epidemic models give you without mutation. So the red lines in both curves represent our predictions. Blue is reality, like if in Twitter network, according to our transmission model, this transmitted, we would get these blue circles. And state of the art, if you will, or what was available before this paper is given by the green plus signs. Although our red line is not a perfect match, still is much, much better than, again, the state of the art. And for high school network, we are a little worse than the Twitter case. And one idea why this might be the case is that that was a much smaller network. Like the number of nodes was much smaller than what we took from this Twitter case. And that's a caveat in many of these types of studies where you have a random graph model or a random network model, and things work pretty well if you look at millions of nodes or tens of millions of nodes, but not so well when you reduce that number to maybe a few thousands. So it wasn't entirely surprising, but it was still good to see that our approach did much better than the state of the art. So this is sort of the end of what I like to present for the PNAS paper, but I like to maybe go through a new line of work, talk a little bit about that as well, and then maybe happy to take questions. So this second line of work is still directly related with the PNAS paper, but we asked the following question. Using this paper, can we say anything about the impact of mask wearing in the spread of viruses? And of course, you may say this has nothing to do with spread of information, but I mean, mask is at the end of the day is something that changes your likelihood of transmitting or maybe taking stuff from others. So I would say instead of mask, you would put some information, correct information out there, and that will effectively act as a mask to prevent someone accepting misinformation as fact and transmitting it. So just an idea out there, but one could potentially put some, build some analogy between, again, the viral spread case and the information propagation case. So with respect to the analogy we looked at between the mask case and the mutations was as follows. We said the following. So what is actually a mutation, right? What does it say for someone who doesn't have any interest in biology? It basically says that I received this virus. The person who transmitted to me had some chance, some fixed chance of transmitting it to me. But I received it and I now have a different probability of transmitting it to others because virus has mutated in my body. And we could argue that mask is a bit similar. If somebody who wasn't wearing a mask transmitted the disease to us, but I am wearing a mask, so I may have a different chance of transmitting it. And you can say the same thing for all four possibilities, like between the two individuals who could potentially infect each other, each one could be wearing a mask or not wearing a mask. So that gives us four possibilities. And essentially four transmissibilities, four chances for the transmission to occur between the two people. And of course, this line of work can be extended to not just one type of mask, but multiple types. And each one is represented by perhaps another strain of the virus. And we looked at this, and we have to sort of build this analogy, right? So one thing is about transmissibility. And we said that transmissibility is something that you could view this way, right? So I am carrying this virus. I have a bunch of contacts. If I pick one of my contacts uniformly at random, what is the expected chance that I will infect them? And that's dependent on what fraction of my neighbors wear a mask, my contacts. And also, of course, it depends on whether I personally wear a mask or not. So if I am wearing a mask, we said our transmissibility is denoted by T1. And for each person I am contacting who wears a mask, I have TMM. M is standing for mask, so both people are wearing in this case. Plus the probability that I am contacting someone who is not wearing a mask, which happens with this probability. And in that case, my transmission probability becomes TMN, mask and non-mask here is used for notation. So the details are not very important, but the crux of it is that there is a direct analogy that one could potentially build between the mutation case and the mask wearing case. And for non-mask wearers, the transmissibility is different. So instead of TMM, they have TNM, and similarly for here. And the last bit of the analogy requires you to map something in the mutation model, that was the mutation matrix, to this particular mask wearing case. And there the argument was that, again, mutation is simply a change of the transmissibility, right? So we could perhaps view this as, what are the chances of someone who got the infection from a mask wearer themselves are also mask wearers? So we could view this as mu11. We could view this as someone receiving strain 1 and also keeping strain 1 and transmitting that with the same probability, same transmissibility to their contacts. But if a mask-wearing person infects a non-mask-wearing person, then we could say that this is almost, not exactly, but almost like a mutation, because the transmissibility will be different. So a non-mask-wearing person will have a different transmissibility after they get the virus and start transmitting it to their contacts. So with this, we can make some simple calculation and get a one-to-one mapping between the mutation and mask models. And it turns out that actually, let me go through this one. Turns out that the predictions we get just using the PNAS paper results, without doing any new analysis, just using the results from the mutation model, we can get perfect match for the mask model, but only for the probability of creating an epidemic. So if you are only concerned about the impact of masks preventing a pandemic, you could just use that PNAS paper results and get a sense of it. I mean, again, admittedly, the work has other assumptions that may prevent you from applying it directly, but from that modeling analogy perspective, it's a perfect match. But for the expected size of the epidemics, when this thing becomes a pandemic and you are asking whether it's going to be 10% or 50% of the population that's getting infected, you can no longer directly use the mutation model if you want exact results. But here the picture shows that you are still very close. So the theoretical is what you get from just the mutation models analysis. Blue circles are the reality. And there is a little bit of a gap. And the mutation model here is saying, sort of it's the theoretical aspect of the mutation model. So you can actually perhaps forget about the green squares for the moment. But the main message here again is that you are not exactly accurate between the blue circles and the red line, but still it is giving you approximate results. And one note here perhaps could be interesting is that the difference is happening here between the mutation and the mask, because as you move along in the pandemic, right, if more and more people are getting infected, it's not happening equally across mask wearers and non-mask wearers. Actually, non-mask wearers, those who do not wear a mask, are more and more likely to be infected. So if you look at your susceptible population, those who haven't received this virus yet, they will be increasingly more likely to be mask wearers. And that change leads you to need to change the mutation probabilities as you go along. And as a result of that, you don't get an exact match between the mutation results and the mask results. So there's a little bit of a difference because of that. But one could directly analyze the mask model and get direct results for that as well. And there's a paper that we have right now working on that. So this kind of concludes the talk. The summary is that I think the main message, if you are just pure misinformation or information propagation kind of researcher, if that's your main research area, I would still say that one useful message from this talk is that mutations are something to perhaps consider in your analysis, in your data collection. Think if at any point somebody making a modification made an impact. You could almost also consider the correct version and the fake news or fake information being two different strains, and maybe look at it from that perspective as well. And the analysis we have done will tell you actually how many people will get strain 1 versus strain 2. And that could be an important maybe result to sort of say under what conditions more people will get the misinformation versus the correct one. But if you are more broadly interested in spreading processes, of course, this work says a lot about transmission dynamics, where you have multiple variants, and potentially say something about the current pandemic as well, and the potential impact of the new variants that we are seeing. And one last bullet is, of course, about the last part of the talk, where I said there is some potential for this work to shed light on the impact of mask wearing as well. So that concludes my talk. Thank you so much for listening, and happy to take questions.
So, Osman, when you were looking in your face mask example, are you looking at the probability of people? I missed whether or not the probability of people wearing the mask was uniform throughout the group, or whether there were also network effects on, like, I wear masks and the people that I like wear masks, but there other people in other parts of the network don't.
Yeah, that's a great question. We have not considered that yet. So we just said it's uniform with probability P. So every individual has a P chance of wearing a mask independent from the network structure. But admittedly, that's probably not a correct assumption, because if you are wearing a mask, you are probably around people who also wear a mask. That's a great point, and potentially can change the entire analysis. Yeah. Should be possible perhaps to incorporate that without too much effort, maybe. I'll have to think about that, but there might be a way to plug it into the mutation probabilities here. Yeah. Because it essentially says what are the odds of, as a mask wearer, you transmit it to a non-mask wearer, and if your contacts have a different sort of distribution in terms of wearing a mask, you could plug it in.
Very much.
Sure.
So the other question is, given this model, I mean, the rate of changes seems so smooth, so you don't really see the kind of jags like you see with super spreader events, right?
Right, we do not. So that's you are probably seeing these plots, right? So these are not time varying plots though. So maybe that's something I didn't make clear. So these are looking at the final size, or even just the probability that this will be a pandemic or not, as we look at different types of connectivity in the population. But you are asking a different question. So if the contact network is fixed and you are like looking at the time variation, do you see jumps and things like that? Our model wouldn't be able to capture that as is, but I think if you look at a time varying simulation, you might be able to sort of incorporate that perhaps. But we didn't focus on we even ignore the time factor, so to speak, in these plots, and looked at just what happens at the end when everything is said and done. I mean, along the way, mutations happen, they may have an impact, but the numbers shown here is just for the final size, or the final status of the spreading process. But it's a good point to sort of think of a way of getting those spikes in the early stages of at least the pandemic. Right now, whatever spreading event happens today can affect the daily cases, but it probably won't affect the total number of infected, right? It's already so high that you can't imagine any event that will create a spike in that, right? I mean, it's 30 million in the US. I guess no event can create a big spike on that, but could be interesting to look at the early stages when it was just a few thousand, maybe.
So I've got a question that was sent to me by email to ask you.
Yeah.
So I'm going to try to sort of read this. So it says, blah, 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 blah. So this is very interesting, but it seems that it's very focused on disease transmission. Is there any indication of what the assumptions, because it is disease, that are driving this result, as opposed to if it were information that was moving through the group or beliefs? Because those seem to flow through different networks differently than disease. So the question is, could I get you to comment on this issue?
Yeah, I mean, it's a great question. So the nature of the work is already sort of kind of abstract from a modeling perspective. We started, of course, talking more about diseases after COVID-19. Kind of the focus shifted a little from the initial motivation. And what also led to this is a bit about the lack of data or difficulties in getting data about mutations, or what you would call as mutations in information spread, right? Like getting the exact timeline of who tweeted what and what kind of changes they made is a little harder from maybe detecting viral mutations. So that led to that type of a distinction. Something this person who asked the question could be interested in, as we are currently working on the model, this mutation model, over a network which has multiple layers. We call it multi-layer, or call it multiplex network. And it's just simply saying that it's being transmitted across Twitter and Reddit simultaneously, or you could say that it is being transmitted in the school layer, coworker layer, and neighborhood layer simultaneously. And potentially, maybe there could be more connections with the information spread there, because we can maybe model individual layers a little bit more accurately and try to see maybe the impact of existence of not just one social network, but multiple of them in this process. But aside from that, it's just captured by a simple probabilistic term. If I am infected, I have this much chance of infecting my contacts. If that's reasonable in information propagation, then you would say this work has some relevance in information propagation domain. But again, confirming via real data the mutation and their impact is, and we talked about it with you also, Kathleen, right? That was a bit hard, so to speak, to get data about. Oh, you are responding via email, I guess, right? That's a hard thing.
Yeah, I typed in your answer and sent it back. So then one of my staff wants to know if we know if we can get decent data on face masks, and we also have case data by state. So discussion about face masks and therefore usage of face masks and so on. Could your model be applied to that real data?
Yeah, that can be useful, I think, yes. We would sort of maybe be a little bit more careful, as you stated, like not just the pure number of people who are wearing a mask, but I mean, to get the exact match between Pennsylvania's transmissions and your model matching that, you would also need a little bit more details about the contact structure, right? Like how many people you are connected with that you can transmit the disease to. But model has an ingredient at the core, the network topology. So we would need that as well. And potentially, if it is the case, perhaps the correlations between your mask wearing chance or you wearing a mask or not versus your friends doing the same, or is it across the entire population? Is it uniform? But I think what the admitted the amount of real data type of work we did showed was that like these types of assumptions and our modeling approach is not exactly matching reality, but you still get close enough approximations that can prove useful in real settings. So I would be interested in looking at the data and see if we can make any reasonable predictions based on that. But even very advanced predictions about, how COVID-19, if you followed any of the predictions, they are constantly updated. And I mean, it's hard, right? People also change their behavior. Viruses change, and saying that I have this model that will match perfectly what's going to happen in the future is not realistic. So, but I think that we can get a reasonable enough approximation with respect to masks. Yeah.
Okay, here's another one. This question that came in. They ask, has Vespiani or any of that group reached out to you to see about incorporating your model into their simulations where they're trying to predict for the whoever it is, doesn't even say, where they're trying to predict for the federals the transmission in the US?
Right, they have not actually, but yeah, that's a good question. We could reach out to them ourselves. But the person who funds this work, so we got an extension on our Army Research Office grants that was initially about just the information propagation on multi-layer networks. Mm-hmm. But they provided additional funding to focus on COVID-19. I know that they work with Vespignani as well. So there is that type of a connection, and we haven't really worked together. And I'm not sure if they must have seen our paper because that person must have forwarded it. But I'm not sure, honestly, if they have incorporated it yet or they are planning to. But it's a good question to follow up on.
Okay, well, if there's no more questions, thank you so much. That was terrific, and we appreciate you being here with us.
Thank you so much, Kathleen, and thanks all for attending.